Okay, it's a great pleasure to be here, and fantastic that Cost, under the heading of Alessandro, put together this great meeting. So I'm going to talk about non-Lorentzian geometry in different branches of physics, field theory, gravity, and string theory. It's based on work with a whole bunch of people. Could have been more of those here, but yeah. If you look at all the names, there's one person here, Jan de Boer, who gave a talk yesterday. So actually there has been quite some progress recently in understanding non-relativistic corners of field theory, gravity, and string theory. And actually, maybe just a word on the word non-relativistic, because it's a little confusing. But I try to, in this talk, when I say non-relativistic, I mean really the Galilean limit that you know from classical mechanics, so speed of light to infinity. And when I say non-Lorentzian, I mean something more general that I hope will become clear in this world. So that's why I say non-relativistic, non-Lorentzian. And this progress builds on improved understanding of underlying geometrical framework, non-Lorentzian geometries. And I hope to make clear in this talk the basics of what a non-Lorentzian geometry is. It's essentially space-times that have local symmetries other than Lorentz symmetry. And non-Lorentzian geometries have, just to give you a watch list, up front appeared in boundary geometries in non-ADS holography. For example, if you do holography for Lipschitz space-times, there are certain deformations of anti-de Sitter space-times characterized by critical exponent. You found on the boundary that it induces a Newton-Cartan geometry, which is an example. It's seen in covariant formulations of post-Newtonian approximations in GR, covariant formulations of non-Lorentzian fluids. So non-Lorentzian fluids would be, for example, the non-relativistic Navier-Stokes, but now put on a curved background, and other condensed matter systems. Horava-Lipschitz gravity, also non-relativistic versions of various 3- and 2-dimensional theories, Chern-Simons and JT gravity. Appears in context of cosmology, black hole horizons, so-called ultra-local or Carroll limit of GR. There are actually interesting connections to double field theory. And then, if you then go to the realm of string theory, there are actually quite some interesting corners of string theory, and particularly there's a non-relativistic corner of string theory that I hope to tell you a little bit more about, and various related corners related to this non-relativistic string theory corner by U-duality. And finally, non-Lorentzian geometries appear when you do certain limits of vanilla ADS CFT, so ADS 5 CFT 4. Okay, that's a little bit of a primer, but so I hope after this talk you know a little bit more what I mean with these words, at least in some specific cases. I've now two also motivational slides. One motivation, and here I really use the word non-relativistic in this sense of speed of light to infinity, comes from considering this cube of physical theories that I'm sure you've seen many times, also called the Bronstein cube, where you have the 3 constants of nature, speed of light, Newton's gravity constant, and Planck's constant. And you know, why many of us are working on a daily basis, and also why we're here, is we want to understand this corner, quantum gravity, and for many people here in this room, string theory is a promising approach there. But whereas we very often think of, let's use the rules of quantum field theory and add gravity to it, or let's start from classical GR and quantize it using what we know how to quantize field theories. There's sort of a third route that comes from this putative corner that I call NR, that we call NRQG, non-relativistic quantum gravity. So if you understand, say, this, that's one motivation. There's maybe like a third way to approach this corner. Now, once you're here, you might wonder, what is this and how does this fit with string theory and holography? And in particular, like, roughly in this corner, holography is a duality between this corner, so string theory, and non-gravitational quantum field theories, like n=4 in this corner. So you could also suspect that if you understand this better, that there might be simpler or novel holographic dualities in this non-relativistic side of the cube. Interestingly enough, okay, it becomes a little bit of a regress. Even the corner of which this is the quantum theory of, namely NRG, sorry for all the abbreviations, but that's non-relativistic gravity, that has some surprising elements. If you would have asked me, because I've actually drawn this corner in my GR class like 14 years ago, I always put Newtonian gravity here, inspire the students, but actually seen as a large speed of light limit or expansion of GR, this corner is actually more general than Newtonian gravity because it includes it, but it also allows for strong gravitational fields while still having non-relativistic tension space symmetries. But then, so this is sort of motivation one, very much related to sort of this non-relativistic side of the cube of physical theories. And if you actually zoom out a little bit more, there is actually a much larger landscape of non-relativistic theories. For one thing, if you could wonder here, there's the speed of light to infinity, so 1/c to 0 going to this corner. But what about sort of strong coupling limits, so the speed of light to 0 here, or h bar to infinity, etc. So, but in particular here, you sort of see another limiting case emerging from this cube. And that's this quite studied recently branch of theories called Carolian theories. We'll say more about that occur in the small speed of light limit. And again, you can consider the small speed of light limit of GR, but also of field theories, etc., etc. Then another point that I think is important to stress here is that beyond the small or large speed of light, there are actually more general limits in string theory. In particular because string theory is so rich, and we actually have many objects in string theory, not just particles, but branes. And that's sort of at the origin that you can do, there's a larger landscape of non-Lorentzian theories, and hence non-Lorentzian geometries that play a role in string theory. And typically they actually related to the vanilla non-relativistic physics by dualities. And then another thing I like to, is maybe kind of technical, but sometimes it causes some confusions. I'd just like to mention it here, and if I have time I mention a little bit more detail, is the concept of, if you play, say, with the parameter c or 1/c, c is the speed of light, the difference between doing limits, like really a limit of a theory, and expansions. I'll say some more about that. Now, what's the common feature of this landscape of non-Lorentzian theories? That they're described on novel curved spacetimes that go beyond Riemannian or pseudo-Riemannian geometry. I call them here non-Lorentzian geometry in the most general sense. And these non-Lorentzian geometries, they then can appear, for example, in new type of gravity actions when you make them dynamical. These NL geometries appear also as backgrounds for relevant probes, and I will illustrate that. And then in addition, that's more like a string theory thing, if you have extended probes, so not particles, but strings and branes, then the physics gets even richer. And not only can the target space be non-Lorentzian, but the wall volume, which is now more than one-dimensional, can also show non-Lorentzian symmetries. I have to speed up a little bit because I was told it's only 25 minutes, but I just want to give a little bit of an example of what a non-Lorentzian geometry is. I will do that by telling you what Newton-Cartan and Carolian geometry are, and then flash some applications. So, Okay. So some of these transparencies I can actually do very quick because they're very simple, but I try to kind of keep it general. We have, of course, all learned in GR that the geometry of space and time is intimately related to the local symmetries of space and time. You know, and this really comes to a very beautiful manifestation in GR, where, following Einstein's special theory of relativity, we insist on that the local symmetries of space and time are Lorentzian or Poincaré. And that's, of course, what gives you a Riemannian geometry. But this link holds, obviously, much more general. So, in a nutshell, what non-Lorentzian geometries are just replace the local symmetries of space and time by some other symmetry group. That's what I call here space-time symmetries. Let's say the bare-bone space-time symmetries that we would like to include. Of course, you could also deviate from that, but are like having time translations and space translations and spatial rotations for isotropic systems. But then, one of the distinctions, and there can be more distinctions if you're in string theory because it's a richer theory, but a first-order distinction of space-time symmetries is obviously what type of boost you have. So what type of relations between space and time do you have? Lorentz, okay, we all know, non-relativistic. We actually, of course, know maybe even better. That's the large speed of light limit. And then the Carroll is the small speed of light limit of a Lorentz boost. It looks like this. So Carroll symmetry, whereas in Galilean space-time, time is absolute. In Carroll geometry, space is absolute. And I will now quickly show you what the geometries are that make these symmetries local. They are known as Newton-Cartan and Carroll geometry. I just say on the side, and some people find it a little bit anachronistic and blasphemic to come throw Aristotle in the game. But, and this is actually a term coined by Penrose, but you could also say, oh, I'm interested in the geometry or the symmetry where there are no boosts at all. And that's called the Aristotelian, and actually has had quite some interesting applications. For example, in non-boost invariant hydrodynamics and in fractal physics. Are there questions at this point? I know there's a 10-minute question session, but maybe there are some burning questions. So, and this is what happens with the light cones, of course, in these limits. 45 degrees flattens out or closes up, and that's why this light cone really closing up. That's why Carroll geometry is also called the ultra-local limit, because things really can only move, in the ultimate limit can only move in time and not in space. So, we'll do this very quick. So, what pseudo-Riemannian geometry is to Poincaré is essentially Newton-Cartan geometry to the Galilean, or more precisely, the Barkman symmetry. I give the Barkman algebra in a second. This, I think, is a very beautiful insight of Cartan, like 1923. So, just some years after Einstein's theory, that he realized, the fact that Einstein geometrized gravity, that's a consequence of, insisting on diffeomorphism invariance. That's not a unique property of GR. You just have to change the tangent space symmetries to Galilean, or rather Barkman symmetry. And he managed to geometrize the Poisson equation of Newtonian physics using that geometry. Now, what's one, by the way, I have very few technical slides, this may be the most technical, but what's one way to think about Newton-Cartan geometry? Actually, in a very nice paper by Andringer, the Groningen group of 2012, is by thinking of, indeed, this local symmetry that you want to have. It's not Galilean, but it's Barkman. Galilean symmetry, of course, we know that you have this commutator, H with boost gives translations. Now, in Galilean symmetry, these would commute, but Galilean theories typically have a mass, and mass is not energy anymore, so you need an extra generator that encodes mass. That's this central element appearing in this commutator. So the algebra together with the mass generator is called the Barkman algebra. And you can, it actually follows from an Inoue-Wigner contraction not of Poincaré, but of Poincaré times an extra U1. Okay, then you can make this local by gauging it, the symmetry and introducing the Bargmann-valued gauge field. And then you can show, and a sort of a trick to, people, half the room might have seen this, how you do this for Riemann in geometry. You change the local translations for diffeomorphism invariance with some trickery. But at the end of the game, you can show that the gauge transformations corresponding to these symmetries here can reproduce the transformations on the local Galilean boosts and rotations and diffeomorphisms. And the metric fields then are the independent fields here. So these connections are dependent, and the independent fields are a time-like Vielbein, a space-like Vielbein, and a U1 gauge field that's dual to this mass generator. And out of this you can make a rotational invariant metric, spatial metric. So, Newton-Cartan geometry, instead of a G mu nu, instead of a metric, you have the objects tau, h, and m, or tau, e, and m. That's what Newton-Cartan geometry is, and then, of course, you have to say how the things transform. This is how they transform on the local Galilean boosts. They are tensors under diffeomorphisms, but they transform in a certain way on the local Galilean boosts. And you can write down the sort of analog of a Christoffel connection. I'm not giving it because it's a little technical, but so you have a Christoffel connection expressed in terms of tau, h, and m, just like you have a Christoffel connection expressed in terms of g. And here's sort of a picture. So there's a time-like Vielbein, there's a spatial metric. Time is orthogonal to space, so h is rank d minus 1 in d dimensions. And there's a gauge field living at every point. And now, if you study more carefully the connection, you actually find that your connection now has an intrinsic torsion that's proportional to the d of tau. Newton-Cartan considered the torsion Lus case, that corresponds to absolute time, but it was not really appreciated, and it came out of sort of holography that you should relax this and allow for torsion. In particular, twistless torsion is sort of the most interesting case. D tau is not zero, but still you have this hypersurface orthogonal condition. Okay, here's then, okay, can give many actions, but here's a very simple action. You can wonder, how does a non-relativistic particle couple to that geometry? Well, there are two techniques to find it. Do a null reduction of a relativistic particle, or do the large speed of light limit of an extremal charged particle. And here you see how the walled line of a particle, x, couples to h, m, and tau. And it shows a covariant kinetic term and a covariant potential term. Just to say, well, you could say, why is this particle even interesting for this audience? But I was told that Jan briefly mentioned the BFSS limit of a non-perturbative description of M theory in terms of D0 particles yesterday. In fact, the D0 particle is an extremely charged particle in string theory. And the matrix string theory on a curved background space-time can actually precisely be obtained from this limit applied to the TBI action of a D0 brane. And in that sense, thanks, D0 branes couple to Newton-Cartan geometry. Just to make the geometry even maybe more intrinsically clear, precisely if you have a more general field theory with Galilean symmetries and you want to couple it to a background field, the background field that you can and want to couple to it is torsional Newton-Cartan. And you precisely have the response to tau being the energy current, to h the spatial stress, and to m the mass current. It's kind of surprising, I think, and of course Son pioneered this from the condensed matter side to describe the fractional quantum Hall effect. It's kind of surprising, I think, from a condensed matter point of view, that these sort of geometric techniques have not been used before. In particular, it's a very nice organizing principle for effective theories and hydrodynamics. What about Carroll geometry? And you might see heard a little bit about it also in different contexts. It's sort of the dual object, I'll just say, essentially you can get it again in the same method I showed you before by gauging the Carroll algebra. Carroll algebra has a different type of commutator structure, namely now translations and Carroll boost commute to the Hamiltonian. And so that's how you then get Carroll geometry. And okay, in view of the time, just leave this. Just say in 1 second that sort of Carroll symmetry has appeared in many contexts, sort of modern contexts, both in terms of gravity, flat space holography, cosmology, and black hole physics. So it's sort of a very nice universal limit, even though it looks a little weird, right, to send the speed of light to 0. I emphasize that limits versus expansions, you have to be a little bit different. In view of the time, let me leave it with that, but then you can ask me what the difference is. Essentially, it has to do whether you want to really insist on canceling divergent terms in the large speed of light limit or some other scaling limit, or whether you like just to get an action expanded. Both have their merits, and they are, of course, well, one is contained in the other, but yeah, it's a little subtle. Again, in view of the time, let me just say that I showed you sort of an intrinsic definition of Newton-Cartan and Carroll geometry, but you can also get it from a large speed or small speed of light expansion of GR, and that has been done very carefully in the last years. Yeah, shows you it's actually a very nice way to get the corresponding dynamical actions on these novel geometries. Because you might wonder, what's the analog of the Einstein-Hilbert action? So you can take the Einstein-Hilbert action, put in a metric, and you sort of, well, you get ready to do the expansion by splitting time and space. This is still totally Lorentz symmetric, but now you assume that these are power series of c squared or 1 over c, and you start expanding. And you can sort of imagine that you can do this, maybe, from the Einstein-Hilbert action and get now gravity actions on these novel type of geometries. And they actually have very nice and interesting properties. Now, in the last part, then, let me say something about string theory. So far I actually talked about particles and some relatively simple symmetries, but Gomis and Oguri found way back in the 20th a very interesting corner of string theory as we know it. You can do it both for the bosonic case as well as the supersymmetric case. And they found an action using a limit that's very similar to what I described, how you get the non-relativistic particle. Namely, you take a near critical limit using the fact. So you now switch on a near critical B field for a string, using the fact that the string is an extremely charged object, not particle, string. And yeah, this is sort of an interesting self-consistent UV complete corner of string theory with the Galilean invariant dispersion relation. Here's the action in conformal gauge on a flat background. And it's actually only recently, well, so in the last 5 or 7 years, that motivated by these advances of understanding non-Lorentzian geometries, that the question was asked, what is the general target space that such non-relativistic strings move on? And there are actually various techniques, but I think the simplest phrase, you can just think about how you did it for the particle. You can either do a null reduction of a relativistic string. Essentially, it has some elements of doing a light-like T-duality along a null isometry. Or you can actually stay in the same dimension, so you not do a reduction, but do a large speed of light limit. And what you find is the correct geometry that now strings, non-relativistic strings, move in. It's some avatar of the Newton-Cartan that I showed you. There's also an underlying algebra that you can gauge. I'll not show it. But it's known as torsional string Newton-Cartan geometry. It actually has a Riemannian geometry in the transverse space that's fibered over a two-dimensional Lorentzian base, and then there are stringy boosts relating the base to the transverse space. Okay, and I just flash here the action. The geometry looks like this. It now has a walled volume field by in the 0 and 1 direction on the walled volume. There's a 2-form potential instead of a 1-form, and this is the action. Okay, I finish in 45 seconds. Just to, I think, well, it's very nice that Jan Rossel will give a talk after this. You can wonder about beta functions and non-relativistic, what kind of non-relativistic supergravities they give. I think Jan will say something about that. There has been a very rich study. And then, yeah, you can wonder, once you have the non-relativistic string corner and have a nice geometric description of this, and you think of it in the context of superstring theory, where we have various interesting perturbative and non-perturbative dualities, you can wonder what kind of other corners can I reach. And here's sort of an overwhelming web, but it's more like to give you the idea that this non-relativistic string theory that I quickly discussed is actually related by dualities to many other corners that have been studied before, like BFSS matrix theory or non-relativistic M theory. But the overarching novelty here is that we now know the target spacetimes on which these different decoupling corners of string theory live. And there are non-Lorentzian target space times. Okay, so then, I could make a longer list, but just to say, on sort of the pure gravity side, because you don't have to be necessarily interested in string theory to look at these things, but on the pure gravity side, there are actually quite some interesting things still to do with this geometric approach and understand post-Newtonian approximations, applications to non-relativistic quantum gravity, explore Carroll's side more, the string theory side that I said, various generalizations. Yeah, and then, so I hope to have made clear that there is some kind of general lesson that non-Lorentzian geometries, even though they sound maybe a little esoteric, that actually are quite a natural tool for study of corners of known relativistic theories. Thanks.
Any questions? Yes.
Can you start with a non-relativistic string and get from it an effective non-relativistic dBi for gauge fields?
Yeah.
And for instance, see what is the deviation of Maxwell theory and try to do some experiment to exclude it or stuff like that?
Interesting questions, and various of my colleagues, there are various interesting papers that have done this by looking at the open string sector of non-relativistic strings, and you find indeed some kind of non-relativistic dBi that actually in the alpha prime to 0 limit becomes a theory that actually was already studied, well, not covariantly, but in flat space decades ago, which is Galilean electrodynamics. So, to say it another way, Galilean electrodynamics actually has a dBi generalization that follows from the open string sector, dBi boundary conditions.
You had 2 pictures of bread somewhere.
Thanks for asking.
I wasn't entirely sure what was...
Thanks for asking. So one picture was your classic bread with the slices, and the other was and very nice you asked it here, was the Italian ciabatta. That's called the first bread with the slices, Dutch bread, and the Italian ciabatta, the Italian bread. So this was to signify that the Dutch bread is flat Newton-Catan space, but you have very nice slices of equal time lined up. What Newton-Catan does is to make it into an Italian bread where the space is curved. Thanks for the question.
Okay, that was not entirely obvious from...
No, I've always put this picture to answer questions. So it has worked for many times.
Another question I had, if you take the non-relativistic limit of ADS-CFT on both sides, do you get a non-relativistic holographic duality?
Yes, it's just, and there have been, there are different sort of approaches to this. I had to skip a slide, but So one approach that we have been pursuing is, because it also depends a little bit how you do the limit. But so one limit that I'm more familiar with, that we see pieces of the puzzle, so if you do a so-called near BPS or scaling limit on the n equals 4 side, then you can implement that on the gauge, on the string theory side, and see that you actually get some, you actually see it's implemented by a double limit on the string theory, both the limit in the target spacetime and the Lorentzian. Okay, so there's sort of a proposal of emergent non-relativistic theory from so-called spin matrix theory. There have been some recent papers by Andrea Fontanella and Nieto that do what you say just more directly, just take any ADS CFT, as we know it, and do a CFT. Yeah, I've not studied the papers in detail because there's some twists and turns that I cannot fully follow there. But it seems a logical route. But one surprising thing, that what I found surprising, if I understood it well in that paper, is that they actually get, on the gauge theory side, this becomes some kind of Galilean electrodynamics with a U1 to the n symmetry, not with a non-Abelian symmetry, but with a U1 to the n.
You should use the microphone.
Sorry. So I found fairly. So the gauge theory is just n factors of a U1 Galilean electrodynamics type of limit that you would get just from taking a standard non-relativistic limit of n equals 4. So it's a very good question, and I think the last word is not being said, but I would hope that in some years there's a clear answer to that, because I would expect there's a really clear duality where you can actually compute things on both sides.
Thank you. Okay, I'll take 2 more questions.
About Carolean limit, I mean, what insight does the Carolean limit give you on a relativistic system? Namely, why should we consider this limit?
Okay, a nice question. Okay, I think the easiest answer is GR is a very complicated nonlinear theory. Any kind of tool that gives us maybe a handle to explore solutions can be useful. Now, and the interesting thing is, and you could also say that's trivial, but because the theory becomes ultra-local, Einstein equations actually reduce to ODEs. Actually, so the leading order action that you get from Einstein-Hilbert is roughly S extrinsic curvature squared. But that's actually quite nice because you can find quite some interesting non-trivial solutions. From, yeah, precisely because it's all.
It's actually similar to EKL in the cosmological singularity.
Thanks for putting that up, because actually Mark Hanaud, in a very visionary paper called the zero signature limit of GR, because if you think about it, it's the same as the zero signature limit, right? Because C squared is in terms of in front of DT squared. He explored this in the 80s while he was at Princeton, and then also in later papers. You can show that a subset of solutions is related to the geometry that you see if you're very close to the singularity of the black hole.
Space
Sorry?
The space lines.
Space-like singularity, just thanks. So that's just one, but I can tell you more interesting applications.
One more question.
You mentioned T-duality in a null direction, so I wanted to ask what that means, because if you use the usual Boucher approach, you find that it doesn't work for a null direction because you have 1 over the norm of the killing vector, which would be 0 for a null vector.
Yeah, so one way to, there's this Seiberg-Sen prescription to see it as a limit, as an infinite boost limit of a space-like T-duality. Well, I can show you the details. There is a way to make sense of it, even using, in fact, the Rorschach for Linde gauging prescription. You just have to take an appropriate scaling limit. I can maybe put it another way. Think about, I don't know if this helps. But actually, non-relativistic string theory, if you do a T-duality, okay, first of all, there are many details I'm going to say. Non-relativistic string theory always needs a compact direction in the longitudinal direction. Because you need to have non-zero winding. You can see that to make sense of the physical spectrum. You can actually show that if you do a regular T-duality along this longitudinal direction of the non-relativistic string, you end up with the DLCQ of type 2 string theory. So so one way actually to say is that, you know, at the expense of non-relativistic target space symmetries, you can get a reformulation of something you don't maybe have doubts about, namely doing the DLCQ. But it's a dual perspective.
Okay, let's thank Niels again for his nice talk.